Okay, welcome back. Last class, we looked at an example of how fuzzy membership can be done, where we had marks of 5 students and a formula like this was designed to indicate the membership function or the amount of uh, the range of values between 0 and 1 each mark is assigned to. And this is how we get the output based on this formula. And this is a graph according to this formula. So just a revision. What is a fuzzy set representation is basically a set A, and usually when it comes to fuzzy set, we use the symbol like A with the underline underneath A. So most of the textbooks that you see, maybe you can see to indicate other than a normal set or a crisp set, to denote a fuzzy set, we can use an underline beneath the letter. That is also a way of representing fuzzy set. So a fuzzy set is shown in such a way that for any element x, it will be associated with a membership function. That is denoted by the mathematical symbol mu. So mu of a of x. So this is a membership function. So an example of a membership function is what we saw here. Just a second. Yes, what we saw here. This is an example of how we can create a membership function. So we learn the types of membership functions in the coming slides. So this membership function mu of a, and then you have for x that belongs to the set of all the elements, or that is known as either U or capital X. It's known as a universe or universe of discourse. So everything comes under this set, and this small x is basically a subset of the entire thing, you can say. Okay. Now this membership value always falls between 0 and 1. Okay. So some more, what to say, the thing that we learned in the previous slide, that is, sorry, previous class, that is the difference between fuzzy set and crisp set. So you can see crisp set usually goes with the Boolean or a binary value like yes or no or 0, 1. But whereas a fuzzy set, you have a set of values associated between 0 and 1. Okay. This is another example where you can see, just a second. So where you can see that the traditional crisp set representation of hot and cold is shown by 70 degree Fahrenheit, whereas in a fuzzy set representation, you can see how they cross over, that is beyond 70 and below 70. This is how the temperature is mapped on a fuzzy set. Okay, next. This is another difference showing the boundaries of a crisp set and of a fuzzy set. A general comparison uh, which shows the difference between fuzzy set and crisp set. You can get even better points than this. So this is defined by precise and certain characteristics in case of a crisp set, whereas in a fuzzy it is vague or it can be ambiguous properties. And in a crisp set, it is either a member of a set or it is not. There's only two options. But the other thing, fuzzy set, it can be partially included in the set. And applications where crisp set is used is, you can say digital logic, because it contains Boolean values for digital logic design and many other similar applications it can be used. Fuzzy set is used in wide variety of applications, like the assignment I gave you. There are different number of in image processing, machine learning, in medical imaging, so many things. So in fuzzy controllers, what to say, autonomous vehicles, there are many applications of a fuzzy set. And of course, it is bi-valued in a crisp set, and fuzzy set is infinite valued. So this is just an example showing how to write down the representation given a question like this. So it's given like a realtor wants to classify the house he offers to his clients. One indicator of comfort of these houses is the number of bedrooms in. Say, for example, if the mean value is universe is given by 1, 2 till 3, 4, etc. till 10, this will be the set of available type of houses where an element is actually describing the number of bedrooms in a house. Okay. Then the fuzzy set that is that I want to create is based on the type. Comfortable house, comfortable type of house for a four-person family. That is a requirement. So how do you create a fuzzy set based on this particular label? Okay. So if I write, if the number of bedrooms in the house is one, just a second. Okay. If the number of bedrooms in the house is one, then we say, or we'll come to this first. If the number of bedrooms in the house is four, then we say it is completely within the set that is, it is the maximum value that is one. But when the number of bedrooms in the house is one, then you can say it is just maybe zero point 0.2. There's no particular formula designed here, but we're just assuming these are the values. So if the number of bedrooms in the house is 2, maybe zero point 0.5 is the level of comfortableness there. Then if it is 3, it is nearing to 1, so it is 0.8. If it is 5, it is not as good as where a four-person family can live in a type of house. If 5 people come in it, then it's not as good as being a complete set part of the set, but it will be something like 0.7. It's even worse than you can say 3 persons. Then 6, when it comes to number of bedrooms in the house is 6, then you can say, sorry, not number of bedrooms, sorry, number of people in the house is, you can say is 6, and you can say it is 0.3. So this is how they have designed. Okay. The same thing can be written over here as the same thing. That we write the membership value first, then we write divided by the x value. Where I told you the x value is basically the number of bedrooms itself. The number of bedrooms is 1. It is not comfortable for a four-person. If the number of bedrooms is 6, it is only this much comfortable for a four-person family. So you can see all of them is the notation we have already seen. It can be written in this format or it can be written in this format. Both are the same. Where don't mistake this plus for arithmetic addition. These are not, this is just indicating sum of all the elements that is as a whole. It's not the arithmetic sum. Okay. Now we'll look at some of the operations and properties of fuzzy sets. So these are some of the properties that we saw in a crisp set also: associativity, commutativity, distributivity, idempotency, De Morgan's law, boundary conditions, involution, and transitivity. So we'll just go through all of them quickly. So this indicates that if you have a fuzzy set P, Q, and R, three sets, then uh, P union Q, the whole union R is equivalent to the union of Q and R, then the whole union with P. Similarly, intersection. So you can see they are associative in nature because a combination of this with the union of this one, or a combination of this with the union of this one, is the same thing. Similarly, intersection of this and intersecting it again and creating an intersection of this with R is same as intersection of this set, combination of this set with the first set, that is P. Commutativity is P union Q is same as Q union P. And similarly, P intersection Q is same as Q intersection P. Distributive in nature. Why? Because this P union intersection of Q and R is distributed like this. So that is what happens when it comes to the other side. It is equivalent to P union Q intersection of P union R. Similarly, the opposite. If you have an intersection here and a union here, P and Q, it will be distributed like this. So you have P intersection Q union P intersection R. Okay. Then idempotency is basically, it is showing that is you do a operation with itself, you get the same thing as the output. Say here P is a fuzzy set and P is again the same fuzzy set. So if you take union of P and P, you get P itself. So this is not the case when it comes to a crisp set. You can say it is something different maybe, but in the union operation in a fuzzy set indicates a maximum value. So you know what is the maximum value, right? Finding the maximum among all the elements. So if you take the fuzzy set P and take and the same fuzzy set again and find the maximum of these two sets, you get the same value itself because there's no change. That is the basic idea. So similarly, intersection when intersection comes, we actually take the minimum. Okay, it's not like how we do in a crisp set. It's a little different in fuzzy set. We'll learn these properties eventually in the coming slides. So P intersection P is basically P. Then we have De Morgan's law, which shows that P union Q complement is nothing but P complement intersection Q complement. Similarly, P intersection Q the whole complement is same as P complement union Q complement. Then we have boundary conditions like P union null set. So empty set or null set is which does not have which have all the association or what is it, the membership function as 0. If all the values are 0, you call it as a null set. That is, there is no association uh, available with any of the members. Then you call it as an empty or a phi set. So P union phi is P itself, and P intersection phi is equal to phi itself. And P union, the universe of discourse will be the universe of discourse itself. P intersection universe will be P. Involution. Involution means you are applying the same function to itself twice. Say for example, a negation operator. In Eclipse, let me know what is a negation operator. If you have a negation like this, so that is a complement or not operation of P. Again, you apply a negation. What happens is negation, you get back the element itself. So the same thing. So that is what is shown here. Involution means you are applying it twice. So P complement, the whole complement will give you P itself. Transitivity is something like this. If P is a subset of Q and Q is a subset of R, then eventually we can say that P is also a subset of R. Now, what are the different operations on fuzzy set? So I'll just list out the ones first, and you can see union, intersection, complement, then equality, inclusion, product, difference, distinctive sum. Actually, these are only some of them that is given in our main textbook, but there are many more if you search other textbooks on the internet. So these are the basic ones. So the basic three ones are these three, that is union, intersection, and complement. Okay. So we'll see what is each one of them in detail. So union operation is basically analogous to the OR operation. So usually when you have a crisp set, what happens is you have a set say 1, 2, 3, and then you have a set 4, 5, 6. Union is basically the combination of all of them, right? So here also union of two fuzzy set, you can see a graph representation of this shows like this. It's everything that comes under the like say if this is a fuzzy set A and this is B, so you can see the red marking that is shown here. Everything that comes under this is basically the union. But the property is written in such a way that union, that is the membership function, how you treat the membership function is here the P union Q, the membership function of a value X, mu of X for P union Q is nothing but max value of the membership function of P for a particular value S and the membership function of Q for a particular value X such that X belongs to the universe of discourse and take the max among each of the element. So for each element X, we take the maximum among P and maximum among the set Q. Similarly, when it comes to intersection, it is minimum of what is available in P and what is available in Q. Okay, so intersection of P intersection mu of P intersection Q of particular element X is a minimum of what is available in P and what is available in Q. Complement will be the opposite. We know that. So we know that the maximum value of a membership function is 1. So 1 minus mu of P of X is what is known as P complement or P dash. Okay, so we'll just look at this is how you can represent a particular graph or the logic. It's analogous to the logical OR operation, you can say. And similarly, because logical OR, we take the maximum of whatever is true. Similarly, when it comes to intersection, it is analogous to logical AND. That is, you take the minimum of what is available. So usually, you can see that the union of two fuzzy set is basically the smallest fuzzy set containing both. Okay, and their intersection is basically the largest fuzzy set contained by both the given set. So containing both means because it is a union, you need A set as well as B set. But whereas in the other one, whichever is the largest given by both the set together, that one will be taken for intersection. So say this is fuzzy set A and this is B. The intersection of this point is shown like this. See this. We'll look at an example. You will understand it better. Uh, Third one, complement. So this is how a complement. You have a fuzzy set A shown by the red line in the graph, and complement of A is 1 minus each of the value that is available in A. So it will be something like this, the blue line. Okay. As an example, say look at the left side. We are looking at union of two fuzzy sets. Okay. So union of two fuzzy sets. So suppose that these are the values in set A and these are the values in set B. So for the element 2, the membership function is 1. For the element 3, it is 0.5. For element 4, it is 0.3. 5, it is 0.2. The same elements are available in set B also. So 1, 3, 4, and 5, and the membership values are given. So according to A union B, we have to take max of each of the element of A as well as from B, set B. Okay, this is how we have to take. So what we can do here is we check if each of the values and see whether okay, just a second. Okay, and see whether which is the maximum among for a value, say for a particular value 2, which is the maximum membership among each of the set. So you can see here 2 has 0.5, whereas here it has 1. So naturally for A union B, I'll be selecting only 1 by 2, not 0.5. Okay. Similarly, you have a combination of, that is the first one we have taken. Now for the other one, the second element 3, what we're going to do is we have 0.5 as well as 0.7. Here we had, and so we did not take this. Okay. Now, whereas for the second one, second element 3, what we did was we had 0.5 and 0.7. We did not take 0.5, so it will be 0.7 upon 3. And the next one, again, we have 0.3 and 0.2. Will not be taking 0.2. Next, for the element 5, we have 0.2 and 0.4. We'll be taking 0.4, but not 0.2. So this is how we'll be taking this. Okay, so this is how we created a union of A and B by taking the max of each element X, the maximum of each element X among the set A and set B. So that is the answer. Okay, now let us come to intersection. This is just the opposite. You have to take the minimum. Minimum of mu of A of X and minimum of mu of B of X. So this is what we do. Now, if we're taking the minimum of 2, we can see that 1 is maximum. So we'll not be taking this. We'll be taking this. For 3, the maximum is 0.7. So we'll not be taking this. We'll be taking the minimum one. Then we have 0.2 and 0.3. We'll not be taking this. Then we have for fifth element number 5, we have 0.2 and 0.4. We'll not be taking this. Whereas taking. So the answer will be 0.5 by 2 plus 0.5 by 3 plus 0.2 by 4 plus 0.2 by 5. So this will be the elements of the set. Okay. Similarly, finding the complement. The equation for finding the complement is, if you want to find the complement of any set, say A cap or A dash, whatever it is, then we do 1 minus mu of A of x. Just do 1 minus like this. So 1 minus is, you can see, taking complement of A. So 1 minus. So 1 minus the membership function of this. So this will become 0. This will be gone. Okay. Then 0.5. So 1 minus 0.5. The remaining is 0.5. 1 minus 0.3. 1 minus 0.2 and so on. So this way we can just do 1 minus the existing value and you get the, so when it becomes a 0, that means there is no more association. I'll show you the output of this. See, like this. It will be 0 by 2, 0.5 by 3, 0.4 by 4. Then I think this is for another example, but it is somewhat similar. So 1 minus 0.7, it will be 0.7, then this will be 0.8 and so on. Okay. Okay. So similarly for B also you can find the complement yourself. Just do 1 minus the existing value. This is another example. Given these values A and B, you can see how this was initially 1 and after complement it becomes 0. So actually there is no more association. Actually it will be out of the set now. A complement 2 is not involved in the set because the association is you can say 0. Then A union B is also shown and so on. Now coming to the rest of the operations, we learned the first three. Next is equality, inclusion, product difference and distinctive sum. We'll see what are these. Equality, you can say two fuzzy sets are equal. Only normally a crisp set, you say it is equal when they exactly have the same elements. Say if you have a set A with 1, 2, 3, then A will be equal to B only if B also has 1, 2, 3. But this is for a crisp set. That is not what I'm talking about. We're talking of fuzzy sets. Equality cannot be concluded by just having the same elements. The degree of membership, that is a membership function mu of that particular element, should also be equal. We cannot just say that A and B are equal only if the elements are equal. So you need to have equal membership functions also. Then we say A, the set fuzzy set A is equal to the fuzzy set B. Okay. Inclusion or containment. So inclusion or containment for any sets, you can say um, for a two-valued set, you can say A is a subset of B if all elements of A are also elements of B. Of course, naturally, a crisp set, this is how we do it. Say, for example, in a crisp set, not a fuzzy, in a crisp set, if you have a value 1, comma 2, then you have a value B is equal to 1, 2, 3, etc. So you can say here A is a subset of B, subset. Why? Because all the values in A are available in B also. That was the basic idea. But when it comes to a fuzzy set, this is not complete. We have to also look into the degrees of membership. So if all the elements have a membership value in A, which the value of all the member elements in the membership value of each element in A should be less than equal to the membership value of the same element in B. Okay, where X belongs to the universe of discourse, capital X. Then you can say that A is a subset of B. So this is how it should look like. Suppose you have a set B, the membership values of set B, if it is looking like this, then the membership value of A should be contained within this. You can see it is entirely inside the membership values of set B. So it should be always less than or equal to. I can show you an example of this. Like before I said, in an inclusion, it's the same thing. Okay, inclusion property, or you can also call it as a containment property. It's the same thing. So in a crisp set, you can say when 2, 4, 6 is entirely contained inside B. That is why you can say A is a subset of B. But when it comes to a fuzzy set, say some you have an example x1 x2, x3 are the three elements. The elements are same in A and B. Okay, but the membership values are different, you can see. So if you have that for a particular element x1, if the membership value in A is less than or equal to the membership value in B, yes, 0.3 is less than 0.5. So that is why it is contained within. Similarly for x2, if 0.6 is less than the membership value of B, that is 0.9, then you can say it is also true. And similarly here it is 0.8 and here it is 1. So you can say that the value is less. So since all of them are less, you can say that A is a subset of B. And the next one is product P into key. Actually, product there's something known as T-norm. There are many types of products and compositions. We'll learn that in detail. So this product that is P dot Q that is given by is basically a very simple multiplication thing itself. So the membership function of the resulting fuzzy set is defined by the product of the membership value of the same element. So if you want to find P into Q, then there's nothing but the membership value of the element in P into the membership value of the element in Q. Say for example, you have x1, x1, x2 and x2 the same elements. So this is 0.5, then this will be 0.8. It's the same element, so you write 0.5 into 0.8, which is nothing but 0.4. Then you have got zero point 0.7 and 0.4, and then you write multiply that and you get 0.28. So this is the answer of product of P and Q. Then we have got difference. So difference is basically P minus Q. So it is equivalent to writing as P intersection Q complement. It's the intersection of the set P with the complement of the set Q. All of you know what is Q complement, right? Q complement is nothing but 1 minus the set membership values of the set Q. We have seen complement of A and B in the previous slides. So assume you have x1 and x2 like this, and you have 0.5 and 0.8, 0.7 and 0.4. So finding the complement of Q is the first step. Finding the complement is 1 minus 0.8, that is nothing but 0.2. Then 1 minus 0.4, that is nothing but 0.6. So finally, you get Q complement as x1, 0.2 is the membership value, and membership value, and x2, 0.6 is the membership value. So this is how you get Q complement. Now, what is the next step? You have to find the intersection with P. So this is the P value. So you can see what was intersection. Intersection was minimum of the elements in A and the membership value in A and the membership value in B, minimum. So in our case, P and Q. So take the minimum of this. So you have x1 is 0.5 here, and here we have x1 is 0.2. So the minimum is 0.2. Here we have x2 as 0.7 and here we have 0.6. So the minimum is 0.6. So you can see hence the answer of P minus Q over here. P minus Q will be x1 0.2 and x2 0.6. Now disjunctive sum. This is something known as a symmetric difference. Symmetric difference is what is common in both of them. That is what we are trying to find out. When you're trying to find the difference of both of them, but what is common, that is what we are trying to do. Like it is defined as the formula is given like this. Symmetric difference is shown by this XOR symbol like this. And you can see it is basically the union of, union of intersection of P with its complement and the intersection of Q with P's complement. So intersection of P with Q's complement and intersection of Q with P's complement and the union of both of them. So whatever is common between P and Q complement and P complement and Q, and take the union of that. So you have a min value to be taken here. You have a minimum value to be taken here. And when it comes to union, you have a maximum value to be taken. So that is how we do it. Say suppose these are the sets given P and Q. Now find the complement of each one of them. P complement and Q complement we need to find. So take 1 minus, so 0.5, 1 minus 0.5, 1 minus 0.7 is 0.3, 1 minus 0.8 is 0.2, 1 minus 0.4 is 0.6. This is the complement. Now we have to take the intersections of each of the opposite complements. So we take, say, so you can look here, the first value here is 0.5 and in the Q's complement it is 0.2. So we take minimum, right, for intersection. Second value has 0.7 and whereas this one has 0.6. So we take the minimum one. Okay. So that is what happens here. You can see 0.2 is taken and sorry, not this one. 0.2 is taken and 0.6 is taken. When it comes to the opposite of P complement, the next one, intersection of P complement and Q, we had 0.5 and 0.8 where we take 0.5, 0.3 and 0.4 where we take 0.3. So these are the values that are taken. You can just see here also. So that is, you have P complement, that is 0.8 and 0.5, 0.4 and 0.3. So we got 5 and 0.3, 0.5 and 0.3. Now next is taking the maximum, that is a union operation of these two outputs. These two outputs, you take the union. You have to take the maximum now. Now which is the maximum on 0.2 and 0.5? It is 0.5, so hence 0.5. Then you have 0.6 and 0.3, the maximum is 0.6, so this is the maximum. So this is how we find the distinctive sum. Okay, so that is all for today.